My name is Christopher Micklejohn, and I'm going to talk about our paper, Method Overloading the Circuit. This is joint work between CMU, DoorDash, and the University of Alaska Anchorage. Microservice architecture is an architectural style where applications are constructed from services that communicate using remote procedure call and are developed, scaled, and deployed independently. Some examples of microservice applications are Netflix, composed of 1,000 services in 2021, Uber, composed of 2,200 services in 2016, where 120 of those were involved in getting a single ride, and DoorDash, which is currently composed of 500 services, where over 100 services are involved in the core flow of connecting merchants, consumers, and dashers. As of 2021, all companies in the Fortune 50 were hiring for microservice development roles. I believe that microservices is the most common and complex distributed application being built today. For example, while Twitter has run extremely large Hadoop clusters, most of the nodes in the system had the same behavior and ran the same exact code. In contrast, each of the services at DoorDash provide different functionality, have a different API, and are deployed continuously, up to 100 deployment events per day. Let's start by looking at what a microservice application looks like. Here, we have Netflix loaded on my iPhone. When this app loads, each of the rows of content are provided by a different service, run on a different number of servers by teams of different sizes. For example, the My List team, the Bookmarks team, and the User Recommendations team. The API Gateway team is then responsible for pulling all this content together to display in an application by issuing RPCs. We build applications this way to improve developer productivity and support application scalability. However, we trade off technical complexity. A single developer now doesn't need to know how to deploy all of Netflix for a minor change, but now has to consider partial failure, specifically by answering the question, what happens when one service is producing errors, and what should happen when that service is producing errors. How do we know what should happen, and more importantly, how do we verify that it does? Let's revisit the Netflix example. In this example, the application graph that supports this functionality is presented here. In this case, Netflix uses a technique called fallbacks, where alternative application logic is executed in the event of a dependency failure. In this specific case, we might imagine something like replacing the continue watching content that comes from the failing bookmark service with different content if the bookmark service happens to be unavailable. Perhaps we'll use content that's currently trending on Netflix. There are many different resilience techniques that developers of microservice applications might employ. For example, retrying requests upon failure, timing out requests, load shedding, or circuit breaking. So how does one verify these resilience techniques? Often developers rely on chaos engineering or other principled fault injection techniques. We presented one such approach at SoCC last year called filibuster. So what does reliability look like at DoorDash? First, we use fallbacks in a similar style to Netflix. When a downstream dependency is unavailable, we load alternative content from different services or rely on default responses in order to allow our application to degrade gracefully. We also use cluster orchestration to support rolling deploys of services. This ensures that there's always a minimum number of instances of each service running at a given time. We use load balancing to distribute requests across those replicas. Whenever a service issues an RPC, if that RPC fails with anything other than a timeout, it will be automatically retried with the goal of hitting a non-failed replica. For preventing against overloads, we employ load shedding at each service, which will short-circuit an RPC with an error, and similarly, we use circuit breakers to short-circuit RPCs at the call site if we have observed failures too often for the target of the RPC invocation. So why are circuit breakers important? Circuit breakers are important because microservice fault tolerance is more complicated and more nuanced than the fault tolerance commonly seen with distributed databases or other distributed systems. For example, in addition to simple crash failures and message omission, which are taken care of by the underlying RPC frameworks and cluster management, developers must also consider the following. First, services are deployed frequently, up to multiple times a day, and sometimes bad deployments happen. In this example, it may be that all instances of a service are returning errors for a given RPC endpoint. This might not be detected by liveness or readiness probes if they're too shallow, and especially if that endpoint isn't exercised before a wide release. Second, services might be deployed with a bug that's only triggered when certain arguments are provided. For example, under certain conditions, a function might experience a null pointer exception or an array out of bounds exception. And third, dependencies of a given RPC method might be malfunctioning. This could be outside of a single service's controls. Its dependencies might slow down, experience timeouts, or fail in other ways that trigger bugs in the service that takes it as a dependency, and therefore, circuit breakers are an important part of our resilience strategy at DoorDash. So why are we here? Well, it's because circuit breakers, as we have observed empirically at DoorDash, can often weaken the resilience of an application by disabling unrelated RPCs. This is an area, and this area I mean specifically circuit breakers, of extremely limited academic study. Very few people are researching circuit breakers. So to understand why this occurs, and to generalize from the specific cases we have observed, we did the following. First, we studied circuit breaker designs to first determine if the errors we were experiencing were related to specific implementations or inherent in circuit breaker design. From there, we performed a multi-case study analysis to build sample applications and demonstrate the issues. We extended our open source application corpus with them, which was published at SoCC last year. And then finally, we proposed 2 new designs of circuit breakers. So how does a circuit breaker work? Well, circuit breakers interpose on the RPCs that are issued between services. For each RPC that's executed, we accumulate counters using a sliding window that record the number of RPCs issued, the ones that have failed, ones that have succeeded, and when a minimum threshold of RPCs is met, and when that number exceeds an error threshold, we short circuit RPCs. Now, some academics have considered load shedding a similar technique as a server-side circuit breaker that has different threshold conditions. And in terms of the actual state transitions that circuit breakers make, they begin in the closed state, they move to the open state when the threshold is exceeded. This is where RPCs are refused. And then they move to a half-open state based on configuration to determine if they should either move to open or closed again based on allowing some RPCs to be executed. From the software engineering perspective, we were primarily concerned with 2 properties. First, transparency. Are the circuit breakers visible in application code and require manual installation, or are they inherited from a VM or other part of the system? Second, where the circuit breakers are installed, or the scope. For example, are they installed in the network using a proxy or VM modification, or in the application itself? In the application, are they associated with the RPC client, method, or placed directly at the call site manually? From here, we were able to discover an interesting third property called sensitivity, or how those internal counters of the circuit breaker are scoped with regards to the application code. Often, as we'll see, this is inherited from the scope. In our first case study, inspired by a real-world use case, we'll consider the case of an order service that, as part of creating, modifying, and canceling orders, must communicate with an auth service using RPC, as shown here. Now, the developers might want to refactor this code to reduce duplication, while also installing a circuit breaker to increase resilience. Here, they use a method explicit circuit breaker because it's associated with the method that invokes the RPC, and is explicitly installed using an annotation by the application developer. However, by doing this, they effectively scope the circuit breaker incorrectly. Now, any bug in any of the auth service methods, create, update, or delete, if a circuit breaker is open, will cause it to short circuit calls to the auth service, and we're referring to all calls to the auth service since that circuit breaker is shared. To achieve the proper sensitivity for these types of faults, application developers must refactor the code back to the original design and apply the circuit breaker at each method that issues a different RPC to the auth service. This leads us to our first key insight called partitioning. Each RPC to a unique method that might fail must have its own circuit breaker. Our second key insight is related. It's called scope partitioning. Scope partitioning basically means that depending on the scope of the circuit breaker, whether it's method, client, or call site, and in this case it's method, the partitioning must be performed with respect to that scope. In our second case study, the developers wanted to extend the previous example to support 2 different order types, delivery and takeout. They can do this in several different ways. We're going to show 3 representative examples here. First, they can create a new RPC method at the order service that calls the same method on a new auth service. So here we've created a new takeout auth service that's specific to takeout. Second way they can do this is they can create a new RPC method that calls a different RPC method on the auth service. Here we parameterize the RPC method to takeout delete, depending on order type. Or third, they can just reuse all of their existing application code and parameterize it by adding the order type to the argument list. This is the option we see frequently taken because of the low overhead involved. The question we have to ask is what happens when the application has a bug that only affects the cancellation method for takeout orders. And to handle this properly, the circuit breaker must be sensitive to the order type. Now, in the case of parameterization by method, and the invoked RPC method that's used through a shared method for issuing the RPC, the only way to provide this is if the circuit breaker is sensitive to the RPC method that's been invoked, or the method it's invoking. We refer to this as path sensitivity, where circuit breakers are aware of the RPC's invocation path. In the case that's frequently taken where the code has been parameterized only through its arguments and where all of the underlying methods that issue RPCs are shared, the circuit breaker must be sensitive to the arguments. We refer to this as context sensitivity, where circuit breakers must be aware of the invoking RPC's arguments. Using these case studies, we are able to establish a decision procedure that informs developers which circuit breaker choice will provide the proper sensitivity. For example, by first looking at a single circuit breaker design and all the ways the application can be parameterized using our example applications, and then by looking at the implications of choosing different types of circuit breakers for that same application. In the majority of cases, achieving the correct sensitivity is not possible using the existing designs, therefore necessitating the need for path and context sensitivity. However, it's not as simple as just a developer understanding the implications of their local changes. The decentralized nature of microservices can exacerbate the issue. Let's see how. We'll start with path sensitivity, where we consider the case of downstream dependencies that are impacted by upstream non-local development. We'll start with 4 services developed by 4 different teams, where Team 2 releases a new service E with some new functionality. E continues to call C and D to get the information it needs, and A begins calling E when it needs that new functionality. Now, Team E is unaware of the fork and is using a shared circuit breaker between C and D, regardless of where the request originates. Now, this is problematic if requests from originating from service E trigger a fault in D because that circuit breaker between C and D is shared. For context sensitivity, we can consider a similar application case, but we're going to release a new version of Service D. This new version of Service D receives some requests that are routed to it based on arguments from A, and both calls use a shared circuit breaker between C and D. This is problematic if only requests destined for D prime based on the arguments provided by A cause errors. Now, without the proper sensitivity, the code must be refactored into multiple methods or clients depending on the scope, which is consistent with our 2 first key insights, partitioning and scope partitioning. In our paper, we provide the following. First, a presentation of our taxonomy and the process we use to identify and classify open source circuit breaker implementations. Second, we provide a full discussion and presentation of case study 1 and 2 with an implementation as an extension to the existing filibuster corpus, which was published last year at SoCC. Third, decision diagrams used for proper circuit breaker selection for these 2 case studies. And finally, a discussion of our proposed implementation strategy, which builds on previous work published at SoCC for providing both path and context sensitivity. We also provide recommendations for how each can be used. In short, we want to favor path-sensitive designs and use context sensitivity only in existing code where we need to retrofit resilience before you can refactor the code. Finally, we provide a discussion of open research challenges based on our survey of circuit breakers and our experience of using them at scale at DoorDash, which we hope will be useful for young researchers. In conclusion, microservices solve a socio-technical problem for organizations building large-scale applications and bring a lot of new application reliability challenges to the forefront. Circuit breakers are one technique for improving application reliability, but are understudied, underserviced by the existing academic research. However, they're critical for most organizations building microservice applications. Their current designs are unfortunately incompatible with the way application developers want to build applications today, and to that end, we propose 2 new designs for circuit breakers, which we believe and hope will be useful for microservice applications and microservice developers. To learn more about microservice resilience, I encourage you to visit our website for Filibuster, our tool for testing reliability, and thanks to everybody who contributed to this project. Thank you.